Welcome to this explainer. Okay, let's just dive right into this. Today, we're going to translate what usually feels like some seriously intimidating 3D algebra into a highly visual, real-world spatial journey. If you've ever stared at a textbook page just packed with X, Y, and Z variables and felt, well, completely lost, don't worry. We're going to build our understanding from the ground up, using the actual three-dimensional space sitting right in front of you.
To kick things off, let's consider this fantastic quote by Augustus de Morgan. The moving power of mathematical invention is not reasoning, but imagination. I absolutely love this, because in three-dimensional geometry, your ability to visualize, to literally imagine lines floating in the room around you, is actually way more important than your raw calculation skills. So today, I'm going to ask you to flex your imagination first, and your math muscles second.
And you know, this reliance on imagination is exactly where this all started. Enter Leonhard Euler, literally one of the most brilliant mathematical minds in human history. People like Euler didn't just invent these concepts to torture us with exams, right? They developed these spatial tools to actually map, navigate, and truly understand the physical universe we live in. By learning this, we are basically learning the source code of reality.
Okay, so here's our roadmap for today's explainer. First up, the building blocks. Second, equations of a line. Third, angles between two lines. And finally, skew lines and distances.
All right, let's get into section 1, the building blocks, foundational vocabulary.
So, to lock down a direction in 3D space, I want you to imagine a line pointing straight out from the corner of your room. It makes a specific angle with the floor's length, its width, and the wall's height. These are our X, Y, and Z axes. We call these angles alpha, beta, and gamma. Now, if we take the cosine of these angles, we get what are called direction cosines, which we mathematically denote as L, M, and N. Basically, taking the cosine of these angles gives us our fundamental directional anchor in 3D space.
But let's be real, working with exact cosines can sometimes get pretty messy. Enter direction ratios. These are simply any three numbers, A, B, and C, that are proportional to our direction cosines. So the really crucial point here is that ratios are just scaled versions of the cosines. They give us an infinitely flexible and often much simpler way to mathematically describe the exact same physical direction. You can multiply them by literally any non-zero constant, and they're still going to point the exact same way.
Moving right along to section 2, equations of a line, drawing in 3D space.
In 3D space, a mathematical line is uniquely determined if you know just two things: one specific point it passes through and the direction it's heading. That's it. So here, our line passes through a fixed point A, which has the position vector A, and it runs parallel to a given direction vector B. Now, an arbitrary point P can slide anywhere along that line, dictated by a parameter we call lambda. It's a beautiful way of showing how a line is totally fixed in the geometry of space.
And that brings us to how we actually write this down. You're going to frequently see these two formats. First, the vector form, r equals a plus lambda times b. It's sleek, it's purely geometric. Then there's the Cartesian form, which breaks it down into the familiar x, y, and z coordinates. The big takeaway here? These are not competing ideas. They're simply two different languages, vector and algebraic, describing the exact same line in space. Depending on the problem you're solving, you just choose the language that's easiest to speak.
Okay, on to section 3, angles between two lines, crossing paths in 3D.
When we analyze an intersection, the math actually becomes incredibly simple if we use vectors. Notice how our two directed lines, OP and OQ, intersect in an angle theta. By isolating just the direction vectors of these two lines, we can use their dot product to easily calculate the cosine of that acute angle between them. It's pretty amazing. All of that visual complexity just collapses into a very neat, very manageable vector formula.
Even better, this math gives us some incredibly handy cheat codes. Want to know instantly if two lines are perfectly perpendicular? Just multiply their corresponding direction ratios and add them up. If it equals 0, boom, they are perpendicular. And what if you want to check if they're running parallel? Just look at their direction ratios. If they are proportional fractions of one another, they're parallel. It literally gives you an instant diagnostic tool without needing to draw a single thing.
All right, our last stop, section 4, skew lines and distances, mind-bending 3D concepts.
Okay, so get this. Skew lines. These are lines in space that are neither intersecting nor are they parallel. They belong to completely different non-coplanar spaces. To really visualize this, look at the room you're sitting in right now. Imagine a line going diagonally straight across your ceiling. Now imagine another line going diagonally down one of your walls. If you extend those lines forever, they are absolutely never going to touch each other, but they certainly aren't parallel, right? Those are skew lines. It's a concept that only exists in 3D.
Because these lines never intersect, there's a literal gap floating between them in space. And the mathematical reality here is that the shortest distance across that gap is exactly one specific, unique line segment that happens to be perfectly perpendicular to both of the skew lines at the exact same time. Think of it like a perfectly straight, minimal bridge spanning between two unaligned highways floating in midair.
Now, I know the formula for this in the source text looks massive and honestly terrifying, but we can break it down into 4 totally digestible logical steps. First, you just identify your starting points and directions from the equations. Second, you find the cross product of the two directions. That's what finds our perpendicular bridge. Third, you calculate the vector between the two starting points. And fourth, you compute the magnitude of the projection onto our bridge to get the actual shortest distance. See, step by step, the intimidating algebra becomes totally manageable. Now, briefly, what if those two floating lines happen to be perfectly parallel instead of skew? Well, the logic shifts slightly, but the math is super similar. For skew lines, we rely heavily on the cross product of two different directions. But for parallel lines, they share the exact same direction vector. Because of that, our distance formula adapts to use the cross product of the distance between the points and that single shared direction. It's the exact same spatial concepts, just applied to a slightly different geometric reality.
Okay, let's pull all of this together. We have gone from simple direction cosines to mathematically bridging the gap between skew lines floating in space. So my final provocative question for you is this. Look around the room again. Now that you know the rules, what other invisible mathematical geometries exist in the physical space around you right now? Keep applying that imagination we talked about at the very beginning, and I promise you, you will never look at empty space the exact same way again. Thanks so much for joining me on this explainer.